All right, so what we're going to do is talk about Laplace transforms. So what is a Laplace transform? Well, it's an operator that is used on a function that has uses later. So here's an example why we would ever care about Laplace transforms. So let's look at this differential equation right here. Now you might remember this as the differential equation used to solve for the charge in an electrical circuit. And sometimes the forcing function is not one of our normal functions. Maybe it's not always a sine or cosine function. Maybe it's something that happens piecewise, like maybe it's 1 volt for the first minute and then nothing after that. So how do we account for this? Or in this case, it's, f of t is equal to 1 for the first 2 seconds, and then after that, it's just gone. So we could use our other methods for solving this differential equation, but it would get very long and very tedious. So the Laplace transform, as we're going to find out, is actually the thing that's going to save the day. So some things about Laplace transforms. It is defined as an integral. In fact, right here, it is the integral of e to the negative st times f of t from 0 to infinity. So the thing we have to be really careful about here is because this is an improper integral. So we have to make sure that s is chosen so that the improper integral converges, okay? So usually, s is greater than 0. There are exceptions, because when s is greater than 0, you have e to a negative power, because t is positive, and then that's going to basically drive every function that's multiplied to it down to 0. So that's what we want. So we do call it a function of s because when we're done integrating these, you're going to notice that we just get an expression in s. And it's not a function that you're going to be plugging numbers into. It's more of a representation. And the thing is, it's easier to manipulate things algebraically than it is to manipulate them using calculus and whatnot. So we go to the Laplace transform to kind of help us with that. You're going to realize through the end of this unit that this is a really fascinating thing and it's very useful. So some properties of the Laplace transform, you can read this, but it's basically values for all values of s for which the integral exists. So again, choosing that value of s so that the integral converges. We say that a function f of t has a Laplace transform if it's of what we call exponential order, meaning that it's bounded by some exponential function, okay? You can choose an alpha and a beta so that the exponential function is always higher than f of t, okay? If f of s is a Laplace transform, this is a really good one. As s approaches infinity, the transform should go to 0, okay? In order for the integral to converge, we need this expression to go to 0 as t goes to infinity for some s. So again, looking at that domain restriction. So let's get into actually finding the Laplace transform of a few functions. And we're going to start out with piecewise functions because that's kind of the use of this thing. So here we go. So looking at this, we know the Laplace transform is the integral of the function times e to the negative st. So looking at this function here, this means that from 0 to 2, I'm integrating 1e to the negative st. And from 2 to infinity, I'm integrating 0e to the negative st. Well, integrating 0 times a function is just going to give you 0, so we don't have to worry about that piece. So we just integrate e to the negative st, which we know from calculus is negative 1 over s, e to the negative st, evaluated at 2 and 0. And that, remember, is t equals 2 and t equals 0, just so we don't plug into the wrong variable. So that means this is negative 1 over s, e to the negative 2s. Now minus a negative is going to be positive 1 over s, e to the 0. So this is going to be 1 over s minus 1 over s, e to the negative 2s. And hey, if you want to impress your teacher, factor out the 1 over s. And that's just a nice, cleaner answer. And that is the Laplace transform. So of course, right now, they're just transforms. So they won't really mean much to us until we actually use them to solve other problems. So let's look at another one here. Let's kind of flip the script a little bit. Let's say it starts out being 0 for the first 4 seconds, and then we jump up to 1 infinitely. So the Laplace transform is going to be integral from 0 to infinity. Now from, not 0 to infinity. From 0 to 4, we're integrating 0. So that's going to be a non-issue. And then we go from 4 to infinity of 1 e to the negative st dt. And again, that integral goes to 0, so we're integrating e to the negative st. Since I want the exponential to drive down to 0 as t goes to infinity, I'm going to say right now that s needs to be positive. That's going to guarantee that the integral converges. So what we have now is negative 1 over s, e to the negative st. Now, I'm going to say we're going to infinity in 4. Normally, you would write the limit notation, select b as your upper limit, take the limit as b goes to infinity, etc., etc. That is proper mathematics. But we've seen enough of these that we know what's going to happen here. So as t goes to infinity, that expression is going to go to 0, because you're going to have 1 over s times e to the negative infinity. And then minus the negative is going to be positive, and we have 1 over s, e to the negative 4s. And your final transform is 1 over s, e to the negative 4s. Who knew? Okay, so there's 2 Laplace transforms. We're going to get into transforming basic functions in the next video. So this is kind of the first in a series, so be sure to watch the rest. Thanks for watching.